name is Damon Thompson with Beckhoff Automation. I'm the software product manager. Today we're going to answer your questions. So we'll dive right in. Start with the first one. How do I create an IoT ready machine with greater data acquisition capabilities without overcomplicating things? That's a great question. I assume this is coming from a product, a machine builder. And in that case, there's a few different use cases. There's always different needs from the machine builder and the end user. And on the machine builder side, sometimes it gets complicated. The machine builder wants to collect data and wants to do innovative services back for the machines from the end user. They want to be able to do remote support, connect to the machine remotely, diagnose data. On the flip side, they also want to sell a machine that will connect to any sort of infrastructure that their end user has, because end users are often, especially large end users, are also wanting to collect data, monitor how the overall equipment efficiency of the machine, do insights on their production environment. So they need to be able to connect, but the machine builder may not know exactly what the infrastructure or what protocols or what ERP systems or what databases the end user is making. So this is a perfect question. It means the machine builder has to be ready that they can sell their machine to the end user and connect to anything. So we started out with a philosophy 6 or 7 years ago with the kind of influx of the IoT movement, where we set out to say, look, we want to support any infrastructure or any software that may want to connect to from our controllers. So it means whether it be OPC UA, which is very common to go to ERP systems, higher level systems, cloud, connect direct database connectivity, even SQL servers, things like that we've been doing for, I don't know, a couple decades. But even now, NoSQL databases like MongoDB, etc. Implementing MQTT, an actual JSON library, you just push in the PLC data, turns it into a JSON structure, or supporting things like HTTP and REST, which can connect to ERP systems, higher level systems, Twitter, Facebook. If you want your machine to tweet, no problem, it's built into the PLC, you can tweet from ladder logic. So we really try to incorporate everything. So I would say some of that is making sure that the control system you're selecting has the flexibility to accommodate all of the end user's needs. And on the flip side, if you do run into a situation where you need to convert, we basically support over 30 different communications protocols. You can add one of our controllers in that'll do a translation from your older controller all the way to whatever kind of higher level ERP, database, cloud connectivity, analytics system you would need. IoT and analytics are finally becoming a reality in industrial applications. What is Beckhoff's approach to IoT? There are a few different approaches. One is just general data collection. So we're doing data collection, do analytics on a higher level system, on a cloud-based system, great. Other ones are, I want to do remote connectivity. So from my engineering tools, sitting at the machine builder, I want to connect to this machine and do diagnostics without having to ship them a VPN connection, without having to fly somebody there and do that kind of connectivity. And then on the database side or the analytics side, there's a couple schools of thought too. One is I just want to collect general every few seconds or maybe even hourly data about how many parts am I running, what's the efficiency on first shift versus second shift, that kind of data. But we see that there's a huge gap missing with only those solutions, and that you also would like to collect cyclic data. Once the machine's connected and you have the network infrastructure in place, also collecting really every PLC cycle and keeping it in a ring buffer. And so then the scenario is, hey, if somebody calls and says, I have a problem in the middle of the night, your machine did a weird thing, no problem. We can go back and look at that data for the last 24 hours and really see every step that the machine's controller was in. Really every state, every variable, and really debug it, even though it never threw an alarm, for example. So that's also a very powerful piece. And then also being able to use those same exact tools that live in the same programming environment and be able to do optimization of the machine. So a machine builder sitting at the machine can look and say, well, why is it that this isn't consistent? Every time I load a part, I'm between 1 and 7 seconds to load a part. Well, I can get more efficiency out of that machine if I can squeeze that down and be always 1 second loading a part. And so we can use these tools to graphically analyze that data sitting at the machine to really kind of squeeze all the performance we can out of the existing equipment. Our company is replacing our current vision supplier. Why should we consider using TwinCat Vision from Beckhoff? We really take a different approach to machine vision processing with TwinCat. Traditional approaches on the market are a few different. So we have a smart camera that has its own embedded CPU that processes the image directly. The limiting factor is you really only get a certain amount of CPU that sits out there. Second one is when you multiply those into multiple cameras, so you have an application with 5, 10, 15 cameras, the cost for each one of those pieces of hardware gets exponentially more. The other approach is have PC vision. So you bring the vision back, you do it on a PC, which is great, you get a bigger processor, but you're a little beholden to the operating system. So when you bring it in, the processing speed is also doing operating system interrupts and different checking network settings and all that good stuff that operating systems do. Another approach on the market today is a hybrid system. So it's a dedicated vision PC, but they're extremely expensive and they only do vision. You can connect a couple of cameras. Our approach is very different. We say, let's just connect the vision camera directly into the controller, bring the image directly into our TwinCat runtime, which is already processing motion control commands, PLC, and then process those image and program it within the PLC environment. So the same language that you know from programming motion, programming the rest of the machine control, is also processing the vision algorithm. One advantage of that is once you have results from the vision algorithm, you can react on them immediately. In fact, in the same PLC cycle that you've got the results back. The other one is, because it's processing extremely quickly in the real time, it's super easy to coordinate those things with motion control, distributed clocks over EtherCAT, things like that. It makes everything, the vision, HMI, everything in one software package, one development environment. So you're not having to manage multiple different software packages, multiple projects for the machine. Everything lives in one project. So because everything's also integrated in that one solution or that one project, we also can access to all the diagnostics tools. So being able to pull the PLC data with the vision data all into the same diagnostic scope tool. And actually to show that, I actually have a video that I brought with me that we'll jump to and it'll really show it graphically. Okay, so in this video, what we're seeing is this is TwinCat running. We see that the green line here is actually a scope trace from the vacuum cup that we see. And then in the background, we see that there's live images coming in through TwinCat Vision using just a standard Gigi Vision camera. And we're bringing those images in and timestamping them very precisely with the data from this vacuum cup. And what we can see is while the vacuum cup's picking, we see this spike, and while not, we see that it obviously goes down. And correlating these things, we can stop and take a look and says, well, hey, I saw this weird spike in the data. What happened? Was it that I picked it up sideways when I went to set it down? Did it slightly tweak on a fixturing? You know, what was going on visually to make that data spike or to make that data have that anomaly? And by pulling these two things together, all in one environment, not being in separate software packages, it really makes the diagnostics so much faster and so much more powerful. How is the trend towards SaaS, software as a service, affecting industrial software and applications? Anything as a service seems to be a giant trend right now. Software as a service being one of them. Other ones that we're hearing a lot of interest from machine builders, our customers, is machine as a service. So, you know, actually not selling a capital piece of equipment, but selling it as a service for operations time. On the software side, we're seeing this in just in our everyday consumer lives with software. So even, you know, if you have Adobe products or whatever it might be, are going more towards a subscription service like Netflix than it would be if buying the software perpetual license like it has been historically. We're also seeing this in our own industry. Then it means instead of, you know, purchasing the engineering tools, for example, and being able to utilize those for years, it's really a subscription. You don't pay, you don't get to use those tools for the next day. It's become a little problematic, to be honest, in our industry because, you know, let's say that there's a machine on a plant floor and it needs serviced 2 in the morning, and the maintenance technician pulls out the laptop and, oh, that laptop hasn't been updated. That's more downtime because he has to renew this license agreement or this subscription. We take a different approach at Beckhoff. The base engineering tools for getting on, troubleshooting, doing scope, diagnostics, PLC programming, safety configuration, network configuration, all that is completely free. Download it from our website, install it. You know, everybody can have a copy on their laptop. There is no renewal fee. All of our runtime licenses for the controllers, the runtimes, database connectivity, IoT, etc., all runs on an infinitely renewable 7-day license. So you can download any of the functions and try them out. Our advanced engineering tools are licensed, but they do have trial versions. So if you want to download it and say, I would like to try this out to see if this is going to work for my application, absolutely. We like that. On the machine side, we take a different approach as well. A lot of the other offerings on the market, they basically sell you an industrial controller, right? A PLC, a box, and there's a list of functions that says this does these 2 protocols, it does up to 10 axes, and it does this. And that's what you get. You need something different, you buy a completely new piece of hardware. And we take a very different approach than most of the industry where we say, look, you start with the CPU that might fit the model for your machine, and you start with some of the components, the software components, the TwinCat PLC, an EtherCAT master, whatever it might be. And later you decide, geez, I need a new connectivity. I need this perfect sensor and it's only available on Profinet. Great. We just enable Profinet in the software, assign it to one of the network ports, and now we have a Profinet master or slave. Same thing with IoT functions, OPC UA, database. We just enable those things in the software. There's not really a need to go buy a new piece of hardware or controller. So it makes it extremely flexible. We also license those things to a licensed dongle. It looks like a USB key or an IO slice. And it means the licenses really stay with the machine. So in 5 years from now, you need to replace the controller. You pull the controller out, put a new controller in. No need to repurchase the licenses. They stay with the machine. How do Beckhoff software tools like TwinCat 3 development environment help tackle growing complexity in machine control applications? Machines are growing in complexity. We all see that. But it also allows, the complexity allows faster cycle times, so we're throughputing more product, or smaller footprints, so we can literally make more product with either less amount of labor or in a smaller facility, which is obviously saving costs. So there's a few things. For Beckhoff, the philosophy's been for a couple decades now, AT and IT, which means automation technology, controllers, motion control, field buses combined with IT, so things like PCs, operating systems, databases, and we've really put those two things together. And we continue that today. So for example, we can accommodate a wide range of skill sets for the people that are developing the machines. Inside the same environment is PLC, ladder logic, structured text, all the IEC 61131, all the way over to C++ programming languages, or bringing in MATLAB Simulink models, or even FMI, FMU from simulation tools. On some of the collaboration side, it's really deeply integrated into kind of any source control that you want because we bake all our stuff into Visual Studio. So using Git or Team Foundation Server, pretty much any source control system, even if you're storing things on GitHub, you can directly in the PLC right click and say check in, commit, get latest version, really cleanly integrated. We really bring all those things together in the source control, comparison tools for merging and branching and sourcing, and other professional development tools that we would see from the IT space or the computer science world. Things like doing a profiler, so you can really profile the code and find kind of the hot paths or what's taking the most CPU, or things like static analysis. So if you have multiple programmers working on a team on the same machine or even on different machines within the same company, we want to keep the coding very consistent. And with static analysis, we can set up rules, say, hey, you must name things like this, you're forbidden to use certain keywords, things that are not returning correct codes, flag a warning or an error, really filling out the professional software development suite. So the TwinCat environment is really trying to help do a great job of bringing all these things together and giving professional tools to help minimize that complexity. Many everyday consumer technologies now use AI, artificial intelligence, and machine learning. When will these technologies start to make a real impact on manufacturing? That's an easy question. Today. So what we're seeing in industry today is some controls vendors are starting to offer some things, but they're pretty closed where there's a set of functions. So, hey, I want to do machine learning, but I'm only going to do it for predictive monitoring. And I only have these choices. It's a bearing, it's a ball screw, maybe it's another mechanical assembly, and that's your choices. Beckhoff, we're taking a completely different approach. We really see the future and the power in machine learning. So our approach is we want to use any training set to do any problem on a machine you can think of. So the training set that we can collect data and that we want to use could be PyTorch, it could be TensorFlow, it could be MATLAB, could be whatever these toolkits to train the machine learning module. And then run that module inside of TwinCat real-time and then do predictions on the application. And let me give you some examples. One, for example, is in the packaging industry. So we're adding a product into a pouch, into a wrap, and the product gets put with some inserts that also go in the same package. Now, when we seal those packages, because it's a flow operation, we're putting in the next product, that seal may actually cut one of the inserts because it wasn't inserted properly. And then when it gets to the customer, the end user, they open it up and the thing's damaged. So we want to be able to detect that very early. Well, when we're sealing that, it's extremely complicated to say, well, if the torque goes up, I must have something wrong. Well, if the torque on the motor goes up, it may just be that the cutter is dull. It may just be that the package, the material is a little bit thicker. So it's really hard to say if the torque is greater than X, I have a problem. That may not be true, especially running thousands of packages per minute. So with machine learning, we can bring in dozens or hundreds of different variables and look at that operation and that cut and see exactly, do I think I ran into something, yes or no? And the machine learning algorithm can give me back and say, yeah, we think you hit something. We might want to take a look at that package separately and not just taking in one X variable. We actually have another video on an XTS system that we'd like to show on the machine learning side of things, a little demo. So we see in this video that the XTS system, we're basically matching up these movers with this conveyor that's coming through. And as they get matched up, it follows it to the end and then rotates back around so that it's ready to do a synchronization with the next mover. Now you can see on one side, we're basically just turning that as fast as we can so it can get in line and be ready for the next thing coming through. However, that means that we're running it as fast and as hard as we can. So we're using the most power and the most mechanical wear. So by implementing machine learning, what we're looking at is, hey, how fast is the next product coming? How many movers are already in place? And then I can plot the most optimal path for that next mover. It says, well, based on all that information, here's the next, the path, the motion profile to get from point A to point B. And we can see here on the HMI that we've really limited how much mechanical wear, the hot spots we see on this, and also how much power we're using. So the mechanics are gonna last longer, you're gonna have less downtime, and overall use less power to make the equipment by implementing a little machine learning in the background. If using machine learning on a machine, does that mean that I have to implement bigger PCs with GPUs to do the machine learning? The answer is no, not really. And the reason is most people, when they think machine learning, they think really big GPUs, training, things in the cloud, big hardware. And if you're training large models, that's true. The training side does need big GPUs. It needs big power to do the training. But once you're running the inference, the trained model, it really doesn't take that much CPU power. So we can run that within our TwinCat real-time environment on the machine control from the PLC. So you can make predictions in microsecond levels. Here's all these different parameters that are coming in, run it through the prediction algorithm and getting results out that you can make very quick decisions on, like what is the most optimal path to get from point A to point B, and plotting that motion profile back. So not necessarily. And then the next question always is, well, what if I want to collect data and continually train and make my model better, smarter? Great. So on the controller, we can either gather that data there or send it back to a central database, maybe to a bigger PC with GPUs that is collecting it not from just one machine, but from all the machines in the operation. And then retraining it. Maybe that retraining happens as an aggregate to the machines once a day, maybe once a week. And then we can simply take that retrained model, deploy it back to the running machines, and the running machines can immediately just reprocess, even on the next product line or the next cycle even, and be able to use that newly trained model. What interesting applications have you seen or implemented with IoT Industry 4.0? Great question. A lot of people are looking for examples on what can be done. You know, how can this help my business? What are others doing? One thing I'd like to point out with this question is he says IIoT/Industry 4.0. Those are a little bit different things, to be honest. So Industry 4.0 is really focused on flexible manufacturing. So being able to do a custom product, maybe ordered online, and that custom product run through a line and a processing line that can process that with any of its customization in lot size 1. That's really the focus of Industry 4.0. And it brings in IoT technologies to help it get that done. So kind of with that thought, one example I can think of is we had a customer that has components that can be customized in their industrial components in literally thousands of different ways. And basically it's ordered online. You can say that I want this in slot 1 and this in slot 2 and etc. for multiple slots. And it becomes very complicated. It used to be that they had multiple lines to do this. What they did was say, well, let's figure out how we can make one line that can make all of these thousands configurations. And from the PLC side, not program in every 1,000 recipes. So what they did was the ERP system actually figures out the order of the processes, generates what needs to happen in the PLC stepwise, and then does an OPC call with a OPC UA method calls to the PLC that says, here's your first step, go do it. Here's your second step, go do it. Here's your third step, go do it. And then from the ERP system side, if they implement a new model or a new process, a new product, they can insert that new option in the ERP system, dynamically generate the background, and never have to touch the program running in the machines. Never have to go out to the machines and run a new recipe. So it was connectivity, it was lot size 1, it was custom products all the way from e-commerce website all the way to production. It was very innovative, and these are kind of some of the things that we've seen that are interesting in the IoT space.